Hi, everyone. So, Monday will be a holiday, President's Day, and so on Monday there will be no lecture, no office hours, no discussion sections. That doesn't mean there will be no discussion sections next week. Discussion sections are generally Monday, Tuesday, Wednesday. We are canceling the Monday discussion sections, but you are still invited to attend a Tuesday or Wednesday discussion section. So if you have a Monday discussion section, then please look at the schedule of discussion sections off the class webpage and see if there's another one that you can make time for next week. Today is kind of the day where we get into the real meat of object-oriented languages. We're going to learn about inheritance. So you recently did Lab 3, and in Lab 3 you modified the S-list class so that you would have a tail on your S-list, and that would make certain operations faster, particularly inserting a new item at the end of the list. Well, we could have accomplished that same result without modifying S-list directly, but rather by creating a new class that inherits most of the properties of S-list while adding a few new ones. And that allows us to only change the methods that need to change while keeping the old S-list intact. So I'm going to declare a new class called a tail list. And instead of writing tail list from scratch to be like a better S-list, or instead of copying the code from the S-list class, I'm just going to have tail list be a fancier version of S-list, a subclass of S-list. And the way you say that in Java is you say that tail list extends S-list. And having done that, because tail list extends S-list, it automatically inherits the methods and fields of the S-list class. So, for instance, the head field, the size field, these two fields are inherited from S-list. And you get them automatically in the tail list without having to declare them again. But we do want to add a new field that was not in the S-list class, because remember the purpose of Lab 3 was to add a tail reference to our lists. And so this is how we do it. We inherit some fields from another class, and then if there are new fields we want for the new extended class, then we add those as well. So now we have a code called taillist, a class called taillist, that behaves the same as the S-list class, but has this new additional tail field that's not present in the S-list class. Taillist is said to be a subclass of S-list. And S-list is said to be the superclass of taillist. So a tail list has three fields: head, tail, size. Now, when you're writing a subclass, it allows you to modify the superclass in a number of different ways. And the important three ways are As you've just seen, we can declare new fields. And it probably won't surprise you that you can also declare new methods. You can add methods to your subclass that were not in your superclass. Now, the third one is in some ways the most interesting and the one that gives object-oriented programming a lot of power. And that is that a subclass can override old methods with new implementations. So we've already seen an example of the first one of these things. Let's try out the third one. Of course, what's the big advantage of taillist? The big advantage of taillist is that you can do insert end faster than you can with an S-list. You don't have to walk all the way through the S-list to get to the end before you can insert the new item. So let's write a new insert end for taillist, which overrides S-list's old slow insert end method. So I start off by writing the signature for insert end exactly the same way I wrote it in the superclass file, slist.java. But now I'm writing it again in the taillist file. Now, you did this in Lab 3, so I'm not going to belabor the point by writing out lots of code. Just take your solution to Lab 3 and put it here. And so now what that does is it replaces the old slow insert end method with a new faster one in the taillist class. The old slow method is still there in the slist class. You can still create S-lists and do insert end the old slow way on those S-lists. But you also have the option to create new taillists and do insert end faster there. Now, although we are replacing this method, there are a lot of methods we're not replacing, and that saves us time and work because we don't have to do them over again or copy them. So examples of methods that we're inheriting from slist and not changing are the isEmpty method, the length method, the nth method, the toString method. Adding a tail to a list doesn't require you to change any of these things, so we don't. So these are all inherited from slist with no changes. And there's no need to rewrite them. Are there any questions about any of this so far? You cannot override old fields, no. You can do something different called shadowing, which I will talk about in a week or two, but it's not really useful and not recommended to do it. Overriding gives you power when you override methods. Overriding fields does not give you power, it gives you confusion. A question here? Yeah, after you override a method, it is possible to evoke the old method from the superclass, yes. And I will show you how to do that in a few minutes. When you use inheritance, constructors work in a funny way that you need to get used to. What happens when you construct a tail list? Well, Java executes a tail list constructor. But the first thing that tail list constructor does is call an S-list constructor before it executes any other code. So, you're always going to have an S-list constructor call, and the job of the tail list constructor is to fix up things that still need to be done after the S-list constructor has done what it does. So, for instance, if I write a tail list constructor like this, we'll do a simple one with no parameters that just constructs an empty tail list, then the first thing that happens automatically, you don't even have to ask for it, is that the S-list constructor gets called, and it sets up the S-list part of the tail list for you. So since we're constructing an empty list, what it's going to do is set the size field to 0 and the head field to null. And then you get to do any additional work that needs to be done to make the tail list be initialized. And that means setting up the tail field. So the work we do have to do is initializing tail and making sure that points to something meaningful for the thing we're constructing. Now, one thing you'll notice is that I say that tail list calls the S-list constructor with 0 parameters, and that's always the default. And that is always the default, even if the tail list constructor has parameters. The tail list parameters are not automatically passed on to the S-list. If you want them to be, if you want to change this default behavior, you can do so, but you have to say so explicitly. And so we can do that as follows. Here's another tail list constructor. Now, if this one parameter tail list constructor is just left to its own devices, it will call the 0 parameter S-list constructor. If I don't want that, then there's a keyword in Java called super that I can use to tell Java which superclass constructor I want to call instead of the default one. So this is a lot like using this at the beginning of a constructor. When you use this, it calls another constructor in the same class. When you use super, it calls a constructor in the superclass. Just like this, it has to be the first line in the constructor. And after you've specified which superclass constructor should be called, then you can go on and do your usual initializing. Now, there is no way to tell Java not to call a superclass constructor. You only have the freedom to determine which superclass constructor is going to get called at the beginning of your subclass constructor. And another thing worth noting is that if the zero-parameter constructor is called by default, and the superclass does not have a zero-parameter constructor, because you only have other constructors, then there will be a compile time error when you try to compile it. So you can't fall back on the default superclass constructor if there is no zero-parameter superclass constructor. Yes?
So when you create a tail list, do you create a tail list and an S list at the same time?
No, when you create a tail list, you're only creating one list. It's just a bigger list that is like an S list on steroids, basically. It has all the powers of an S list, but it's still only one object.
Because it calls a super constructor.
It calls a superconstructor, but that doesn't mean there's an S list inside the tail list. That means that it's a bigger form of S list. It's still an S list, it's just like, an S list with 4 ears instead of 2. It's a super S list. Other questions about this? Mm-hmm. Absolutely. So the question is, in these constructors, suppose you don't like what the superclass sets head and size to. Can you change them? Absolutely you can. You can't stop the S-list constructor from originally assigning the wrong values, but you can replace them right away. Other questions? Over here. The superclass has a default constructor if you don't write another constructor. If you write an explicit constructor in the superclass, the default constructor goes away. Sometimes you want to override a method, and yet still you want to be able to call the method that you overrode in the superclass. Especially, sometimes you want the new overriding method to be like the original method with something extra. So for instance, let's look at the insert front method in the S-list class. The insert front method in the S-list class works pretty well, and we want to do pretty much exactly the same thing in the tail list class. There's just one thing wrong with it, which is it does not update the tail. But other than that, it does everything right. So we kind of want to keep it, we want to augment it. So what I'm going to do is in the tail list class, I'm going to override insert front by writing out exactly the same signature here. But my subclass insert front is going to call the superclass insert front. By writing super.insertFront obj, that's calling insert front in the superclass. And that superclass insert front will add the item at the front of the list like it's supposed to. The only thing it gets wrong is it doesn't update the tail pointer. There's actually only one case where you do need to update the tail pointer. When you're inserting at the front of the list, it usually does not change the tail. The exception is if the list was empty and now it has one item, then that one item is now the tail and the head all at the same time. So we need to check for that special case. And we can do that after we run the superclass insert front. We just check if the size of the list is now 1. And if it is, then we need to set up the tail node to be the same as the head node. And that is the only case where that needs to change. And that's the end of my tail list class for now. Questions? Back there? No, it does not. So it's different than constructors. So this super.insert front does not need to be the first statement. That rule only applies to constructors. Any other method you can call at any point in the subclass method. You can call multiple times. You can call different methods, not just insert front, but any method in the superclass, and so forth. So that's a lot more flexible. Yeah. You cannot do super.super. One thing you cannot do is get access to a grandparent method if the parent overrode the grandparent. Java does not allow multiple inheritance, and this is one of the reasons why, to prevent that kind of confusion that would arise in languages that do have multiple inheritance. Mm-hmm. If superclass was not what? If you're saying, are you talking about a class whose superclass is the object class? Dot what? Mm-hmm. Uh-huh. Actually, super does refer to an object, technically. So when you use the super keyword, this is actually a reference, but it's the same reference as this. So in a sense, you can sort of think of, in your stack frame, whenever you have a variable called this, you also have a variable called super. They're both the same variable. It's just that when you invoke something on super, you're invoking it from the super class instead of from this class. Yes? In a subclass, you're asking, are there private methods? No, the subclass cannot access anything private in the superclass. Which brings us to our next topic, actually. So I lied when I said that we do not have to change the slist class. There actually is one change we need to make. You see, the head and the size fields in the slist class were declared to be private. That's not a good idea because the subclass can't read anything that's private in the superclass. Fortunately, Java has more than 2 levels of protection. Private is the most private level of protection. Public is the most public level of protection. There are 2 other levels of protection between public and private. One of them is called protected. There's one more called package that we will learn about later when we learn what Java packages are. But protected means something is readable by the subclasses, but it's private everywhere else. So a class can only read a protected variable if it's in that class or if it's in a superclass of that class. So what that means is, I guess I do want to be here. What that means is we have to go back to the slist class. And declare head and size to be protected instead of private. And then everything else is the same. Yeah, I'm going to write it down now, actually. So a protected field is visible everywhere in the class that declares it and all of its subclasses, but it's not visible in any other class. Private fields are not even visible to the subclasses. So if I had left the head and size fields private, then I would not be able to compile tail list. The compiler would complain that it can't find the head and size fields when I try to compile the insert front method. As a general rule, when you write an abstract data type, if you can imagine any circumstance where someone would ever want to extend it, you probably want to declare most of its private fields to be protected instead of private. You should probably only use private when you're either sure no one will ever want a subclass of this class, or when you're sure that you don't want the subclasses to be able to meddle with that field. Other questions about this? Does what need? Yeah, protected fields can be read and written by the subclass. Yeah. You generally cannot guarantee that the subclass enforces the same invariance as the superclass, that's right. Usually you do write the code so that you try to enforce them, but when you're writing the code for the subclass, you have a lot of power to screw up the superclass. No, by default, fields get package protection. And I can't explain to you what package protection is until we learn about Java packages, probably next week or the week after. So in Java, subclasses can have subclasses of their own, and subclasses are transitive. And in Java, you can wind up with a whole hierarchy of objects or of classes, and the top of the hierarchy is always called object. Object with a capital O is the big daddy superclass of all of the other classes. And that includes classes that are built into Java like string, and classes that you define yourself. And so you can break down classes, subclasses, by giving them classes of their own. And you can break down those subclasses by giving them subclasses of their own. And the point I want to make here is that since, for instance, student is a subclass of proletariat, which is a subclass of worker, therefore student is also a subclass of worker. And since object is a superclass of worker, is a superclass of bourgeoisie, object is also a superclass of bourgeoisie, and so on. And so that's why we usually make our item fields to be of type object. You can store any object whatsoever in a field of type object. And so object is just your natural choice for things like lists, at least until we learn about Java templates. Any questions about that? Mm-hmm.
Does the object have any fields of its own, or is it really just there to serve as sort of the universal superclass for everything?
I don't think object has any fields of its own, but it does have methods. ToString is one that you've seen before. Dot equals is one you've seen. So there's several different methods defined on it. Next, I want to talk about dynamic method lookup. And this is what makes object orientation interesting. This is really the heart of object-oriented languages and what gives them certain powers that other declarative languages like C and Pascal don't have. So, first of all, understand that because tail list is a subclass of slist, every tail list is an slist. And what that means is that anywhere where a program is expecting an slist, you can give it a tail list object, and it should work. So, for instance, I can declare a variable of type slist, and I can assign it a tail list object. Because every tail list is an slist, anywhere where Java is expecting an slist, like this variable s, I can give it a tail list object, and Java is expected to deal with it as if it were just another slist. This does not work the other way around. Not every slist is a tail list. So this first line of code will compile and run, but if I try to do it the other way around, if I have a variable that I declare of type tail list, and I try to assign it a new slist, Java doesn't like that because an slist object is not a tail list. And so you get a compile time error. And you can't compile that line of code. So we're going to have to differentiate between two different types of a variable. So memorize the following two definitions because they're going to be really important to much of the things we do in this class. We can talk about the static type of S. And the static type of S is what we declared it to be, S-list. But we can also talk about the dynamic type of S. This is the class of the object that the variable references right now. So in the moment after I execute that first line of code there, the dynamic type is going to be taillist, because I just constructed a taillist object and stored it in S. So S now has a reference to that taillist object. The reason for these names, the static type is called the static type because it never changes. Once I declare S to be an S-list, S has static type S-list forever. The dynamic type can change all the time. So one moment I might say S equals new taillist, so now its dynamic type is taillist. A line of code later I could say S equals new S-list, and now the dynamic type is S-list. So the dynamic type can change every time I reassign a variable. Just as a shorthand, a lot of the time I'm just going to say type for static type and class for dynamic type when I'm talking about what a variable is. Question?
So even if x equals 4, do we have a dynamic type?
No, primitive types, you don't really have the concept of dynamic type. So this does not apply to primitive types at all. It only applies to reference types. And I should mention that you can also set S equal to null. When S is null, then it doesn't have a dynamic type. Okay, now, when I talk about dynamic method lookup, I'm referring to the following principle. When we invoke an overridden method, Java has to decide which version of the method it's actually going to call. There are several different insert front methods. Which one should I call? Java calls the method for the object's dynamic type. And the static type doesn't matter. And that principle is what's called dynamic method lookup. So when I say dynamic method lookup, I'm referring to this principle here. I should mention that the static type does matter when you're trying to get your code to compile, but once your code compiles, at runtime, when your code is running, Java chooses which version of the method to call based on the dynamic type, whatever it happens to be right now. So let's look at an example of that. Here's static type S-list. I'm going to set S to be a new taillist. And now I'm going to call s.insertEnd on some object I happen to have lying around. What will this call? This will call taillist.insertEnd. And the reason why is because at this moment, S happens to be pointing at a tail list. But I can change that. Now I can make S point at a new S list instead. So here's a new S list. And I overwrite the old value of S with a reference to this new S list. And now I call insertEnd again. Now, please note that this is exactly the same line of code I just executed 2 lines ago, but this time it does something different. It calls slist.insertEnd, an entirely different implementation. And so that is dynamic method lookup. Java automatically looks up the right version of a method to call at runtime, because you want a different method to add an object to a shopping list than you want to add an object to your shopping cart. They're entirely different operations, but you might have the same program calling the same method on both different types of thing, shopping carts and shopping lists. Now, it takes some practice, usually with object-oriented programming, to get a feeling for why dynamic method lookup is so important, but I will try to briefly explain it now, and hopefully it will sink in over the coming month or so. I'll give you a couple of examples. Suppose that you have written a method, and this method could be in any class, that sorts an S list, but only does it through the slist method calls. It uses the public interface of slist to sort the list. What's that? You know, it doesn't actually matter whether you're sorting in place or returning a sorted copy of the list, as long as there are public methods of the slist interface that allow you to do that. So if you have a method that takes an S-list as input and either outputs a new sorted S-list or sorts the existing S-list in place, either one, doesn't matter, then now you have a method that sorts tail lists too. And the great thing about this is that the sorting method might have been implemented long before the tail list was implemented. The person who wrote the sorting algorithm didn't know tail lists would ever exist, but still that code that got written sorts tail lists too. I want to give you a second example as well, but this one I'll just tell you, I'm not going to write it down. Suppose that you've written a class, let's call it run length encoding, that uses S-lists extensively. But then one day you write a tail list class that's faster than the S-list class, and you want your run length encoding to take advantage of that extra speed. Well, all you have to do is change the constructor in your run length encoding so that instead of new S-list, it says new tail list. And now you automatically have the faster performance of tail lists in your run length encoding without making any other changes to the run length encoding class. So object orientation is a way of trying to make different classes that can substitute for each other as easily as possible, including ones that haven't been written yet. So that when you write your tail list, you can replace all your S-lists with tail lists with as little effort as possible. Any questions about any of that? Mm-hmm. Why do we have to what? Why do we have to declare the static type? So there is one big advantage to declaring the static type to be S-list here, which is that Java knows that every S-list has an insertEnd method. So suppose that instead of declaring this as S-list, let's just suppose we had declared this as to be an object. Well, the first line will still work. You can construct a tail list and store it in an object variable, but this second line of code will not compile. S.insertEnd won't compile because not every object has an insertEnd method. There is no insertEnd method in the object class, so Java won't compile this. You can only call insertEnd on a static type that always has an insertEnd method. Question? Yeah, an overriding method can have a different return type. The return type can be a subclass of the superclass's return type. And I'll ask the TAs to talk about that more in discussion section. Other questions? Mm-hmm. I'm sorry, I really can't hear you. Can you talk a lot louder, please? Right. When at runtime, it doesn't matter. Say that louder. Well, what I just said about is at compile time. So there's a big difference between what happens at compile time and what happens at runtime. At runtime, Java just does dynamic method lookup and decides which method to call. But at compile time, Java wants to make sure that you never call a method on a class that doesn't have that method. So compile time is when Java checks and says, does this variable always have an insertEnd method? And if it doesn't, it won't compile it. But once you get past the compiler, and now you're running your code, then dynamic method lookup does not care about static type. Once the code is compiled, the static types, it can basically throw them away. So there are a lot of little subtleties of inheritance that we need to work out now, because this is all kind of complicated. So I'll list 3 of them. Subtlety number 1, suppose we write a new method in the tail list class, and it's called eattail.com. Where's my head? So this will demonstrate the problem we were just talking about again. If I want to call eattail on a variable, that variable has to be guaranteed to have an eattail method. And so that basically needs to be a tail list. So if I write tail list t equals new tail list. And then I write t dot eat tail. Then that compiles and runs, no problem. Now suppose I declare a variable of static type slist, but I make it point to a tail list. So the dynamic type is tail list, just like it was before. So we know that since it's a tail list, it has an eatList method. And now I call s.eatTail again. Well, now I get a compile time error. So what just went wrong? Well, S has static type slist. Not every slist has an eatTail method. So Java will not compile this code unless it's assured that there is always an eatTail method for S. And of course, the line of code above assigned it a tail list, but Java doesn't notice that. Java basically compiles on a line-by-line basis. And all it knows is that not every slist has an eatTail method, so it's not going to compile this line of code. And part of the issue here is that because not every slist has an eatTail method, Java can't use dynamic method lookup to figure out which eatTail to call. So if you want to call eatTail on that tail list, you either have to give it a static type of tail list, or you have to define an eatTail method in the slist class. Sorry, say that again? Mm-hmm. It is absolutely, yes, an option to just define a dummy eatTail method in the slist class that does nothing or returns an error message or whatever. But there are situations where that is not an option, like if somebody else programmed slist and you're not allowed to change it. Mm-hmm. Not every slist has an eatTail method. Oh, did I say? Yeah. Mm-hmm. Is it? Not every slist has a what? Did I write the wrong thing somewhere? Or I'm sorry, I'm having difficulty hearing you. Right. slist having a tail list. So tail list is a subclass of slist. So when I construct an slist, that does not have an eatTail method or a tail list at all. All right, I pointed out earlier that you cannot assign an slist object to a tail list variable. An slist is not a tail list. The rules get more complicated when you're assigning one variable to another. So, suppose I have two variables. S has static type slist, T has static type tail list. And now I assign a tail list object to T. So T also has dynamic type tail list. And now suppose I write S equals T. So I'm assigning something of static type tail list to something with static type S list. Every tail list is an S list, so this can always be done. So Java is happy. It will compile and run this code. But now suppose I try to do it the other way around. Suppose I say T equals S. Well, not every S list is a tail list. So Java doesn't like this statement. It gives you a compile time error. Java doesn't want to take the risk that you'll take an S list that is not a tail list and store it in T. But, we just made T point to a new tail list. We know that its dynamic type is tail list, so it should be safe to do this. So what I want is a way to reassure the Java compiler that it's okay to assign S to T. And Java will let you do that as long as it's sure you know what you're doing. And you assure it by writing a cast. That says T equals tail list S. So this cast is my way of saying, Java, baby, you can trust me. I'm going to get you a tail list so fine. It's going to be the most beautiful tail list you ever saw. You can count on me, baby. I wouldn't let you down, girl. And gonna take you to the end of the rainbow, you and me, girl. Java listens to my reassurance that this really is a tail list and thinks about it a moment and then says, okay. And she goes ahead and compiles that code for me. And when we run that code, yeah, that really is a tail list. S points to a tail list. And so I fulfilled my promise, and everybody is happy. Question? Say that louder, please. I couldn't make out a word of that. I'm sorry. Yes. Oh, are the parentheses necessary? Absolutely. So essentially, those parentheses there, that's how you say I'm doing a cast in Java. It's also how you say I'm doing a cast in C and C++. So you do have to have those parentheses always. That's the syntax for cast. Mm-hmm. We're getting to that next. So, yeah? Can you pass more than one variable? Oh, cast. So you can cast as many variables in an expression as you want, but you don't use a comma. Think of a cast as being a monary operator like the negative sign. If you have a number and you want to make it negative, you put a negative sign in front of it. If you have a number of one type and you want to cast it to a different type, you put a cast sign in front of it, just the same as a minus sign for a negative number. Say again? Well, it doesn't make sense to just have space and another cast. You need to do something with those two references together. How do they relate to each other? All right. So, now that we've established how gullible Java is, let's find out what happens if I blatantly lie to her. So this time we're going to write S is a new S list. So now the dynamic type of S really is S list. And now I'm going to do the same thing I did before. So again, notice I'm doing the exact same line of code I did before. Remember how it was last time, baby? This time it'll be even better. And for the same reason that Java compiled this before, Java will compile it again. It trusts my reassurance that at runtime, that variable S is going to turn out to be a tail list. And so this compiles, and everyone is happy until the code runs. And then when the code runs, you get a runtime error. It doesn't get caught at compile time, but at runtime, you get a very specific exception thrown called a class cast exception. And you'll want to memorize this term because you're probably going to see this a lot this semester. And you're going to want to remember that this is what is going wrong when this happens. But this class cast exception is basically Java's way of saying, "You bastard, you lied to me." Of course, by the time that happens, I've already moved on to the next compiler. Problem solved. So again, the reason why Java rejects this code is because not every S list is a tail list. But if you give reassurance that you know what you're doing, Java will go ahead and compile it. But Java still installs a runtime check so that if you are lying, it will find out when the program actually runs. There are other places you might want to need to use this, like, for instance, a lot of the data structures we have return objects, like our lists. When you get something out of a list, it's of type object, but you might want to use it to do something more specific. And so, for instance, if I want to use the object that is returned by the nth method on my lists, well, nth returns an object just of type object. If I know that object is an integer object, and I want to extract the int value out of it, the first thing I might think to write is, well, let's get that object, and let's call the int value method on it. Because int value is supposed to return the primitive int value of an integer object. But that doesn't work. And again, the reason is because nth returns object, and not every object has an int value method. Integer objects have an int value method. So you need a cast. And this one's a little tricky because you have to put the cast in the right place. You don't want to cast t, you don't want to cast int value, you want to cast the thing in the middle, nth. So you're going to need an extra set of parentheses to do that. So I have a cast to an integer object with a capital I, and I put that cast in front of t.nth1. And then I need to take that whole thing and put it inside parentheses before I call the int value method. So that forces Java to do things in the right order. First it calls the nth method, then it casts the result from object to integer, and then we call int value on that integer object, and every integer object has an int value method. So now Java's happy. This compiles, this runs. Any questions about any of this? Mm-hmm. So pretty much. So I mean, we can go through this quickly. Here's S. Here's T. This line makes T point to a tail list object. The next line makes S point to the same tail list object. The next line is just trying to assign it back, but of course that was a compile time error, so that doesn't work. The next line successfully copies S into T, so T gets overwritten by a new copy of the same reference. The next line creates a brand new S-list object and repoints S to that. And then the last line attempts to make T point to S-list, but Java will never, ever allow something of static type tail list to point to a general S-list object. So there's no way you can ever copy that reference into that box, no matter how hard you try. You're welcome. Other questions? Mm-hmm. Is it possible to what, a subclass? Remove methods. Not really, no. You can, if you don't like a method in a superclass, you can always override it and print an error message, but that's about as close as you can come. Mm-hmm. Mm-hmm. There sure is. That is the next topic, actually. So Java has an operator for this purpose of figuring out what class something is. And that operator is called instance of. And one thing that always throws people off is that the O is not capital. This is a lowercase o. If you write a capital O, you will just get a compiler error and wonder what's going on. And the reason why it's lowercase is because this is an operator built right into the Java language, and by tradition, Java operators are all lowercase. And so the way the instance of operator works is it tells you whether an object is of a specific class. And so, for instance, if I have S is of static type S-list, and I want to know whether it's pointing to a tail list or not, then I can say if S instance of tail list. And so I can use this, for instance, to figure out whether or not it's safe to do a cast. If this Boolean is true, then it's safe to go ahead and do a cast from S to type tail list. Now, the way instance of works is that it returns false if S is null or doesn't reference a tail list. With subclasses of tail list being considered tail lists. Or in other words, it returns true if S references a tail list object or an object that is a subclass of tail list. Other questions about that? All right, let's talk about the equals method, which is another way of overriding, another example, pardon me, of overriding. So equals is a pretty important method, used a lot, and every class has one. Exactly. That's why every method has one, or every class has one. The reason why every class has one is because if you don't define one yourself, you inherit object.equals. Now, object.equals isn't the world's super most useful equals method. It's essentially the same as reference equality. So the default is that R1.equals R2, where R1 and R2 are two different references, is the same, or returns the same Boolean value as if you'd just written R1 double equal sign R2. By the way, I should say these are not exactly the same. There is one big, very important difference that some of you have already run into while trying to do your assignments, which is that when you use dot equals, you will get a runtime error if R1 is null. If you are trying to compare a null, or if you're trying to determine whether or not a reference is null, you have to use the double equal sign to figure out if it's null first. Once you know it's not null, then it's safe to call dot equals. Having said this, the default equals method isn't usually what you want with more interesting classes. Many classes redefine equals to compare the content of the objects instead of just their addresses in memory. So an example of that is the integer class, again, integer with a capital I. And that's in the java.lang library, the one that gets imported automatically. And what this class does is it just stores one primitive int as a private field. So if you compare two integers with the dot equals method, it tells you whether they contain the same primitive int. So like, for instance, if I have an integer object that contains a 7, and here's a reference variable I1 that points at that integer, and I have a different integer object that contains a 7 as well, and I2 points at that, well then, if I write I1 double equal I2, that's false. But if I write I1 dot equals I2, that's true. Because the folks who wrote the integer class redefined, overrode equals to compare the content of the objects instead of just the references. On the other hand, of course, I can have two different variables pointing at the same object, and in that case, both of these are true. I2 double equal I3 is true. And if they have the same content, then if they're actually the same object, then they must have the same content. So integer is just a very simple example, though. You can have multiple levels of equality, and different levels of equality are appropriate for different types of classes, which is why dot equals usually has to be written on a class-by-class basis. So let's look at 4 different degrees of equality that we might want to implement. We've already seen the most simple-minded version of equality is reference equality, which means you just duplicate the functionality of the double equal sign, and that's the default you inherit from the object class. What integer does could be called shallow structural equality. Where 2 objects are dot equals if all of their fields are equal in the primitive sense of the double equal sign. So if 2 ints have the same int value field, then they're equal to each other. But where shallow structural equality might not always be appropriate is in things like lists. So if 2 lists have all their fields equal, that means they both point to the same list node. In practice, you're not going to have 2 different lists that have the same head list node, but you might have 2 different lists with different list nodes that have the same content. So we'd like to have a way to test for that as well, and that is called deep structural equality. And here you say that 2 objects are dot equals if their fields are dot equals. So that means your slist dot equals method might call slist node dot equals, and that might call item dot equals and another slist node dot equals. And you can wind up with a recursive definition where you keep calling a recursive bunch of dot equals methods. We'll see in a second a way to implement that that's iterative and not recursive. But the main point is that deep structural equality tests whether 2 lists have the same content, like the same numbers. It doesn't test whether they both start with the same node in memory. There's also a 4th degree of equality, which is a bit more fuzzy because it really varies from class to class, and we call it logical equality. And logical equality means that you actually ask, what is the meaning of my data structure? Do 2 different data structures have the same meaning? And to clarify what that means, let me give you a couple of examples. First of all, let's think of mathematical sets. If I have 2 different objects that represent a mathematical set, then they should be dot equals if they contain the same elements. And one thing you know about mathematical sets is that a set is considered to be an unordered group of things. So it doesn't matter what order you list the things in. The set 2, 3 is the same as the set 3, 2. So set equality is not the same as list equality. 2 lists are considered to be equal if they have the same items in the same order. 2 sets are considered to be equal if they have the same items, period. Another example is fractions. You'll recall the fraction class from Lab 2. Well, the fractions 1 over 3 and 2 over 6 have the same meaning. So they should be dot equals, because they're both the same number. They don't have any digits in common in their numerators or denominators, but they're still the same number, so they should be dot equals. Yes?
So you said that for deep structural equality, fields are not equal.
Mm-hmm.
Does that mean that deep structural equality is recursive equality?
Yeah, so deep structural equality is kind of a recursive definition, yes. So given these 4 choices, you might ask, which one should I do? It really depends on your data structure. Different data structures have different needs. So the dot equals method may test any of these 4 levels of equality. You have to figure out what your application actually needs and what makes sense for your application. So what I want to do now is do deep structural equality for S-lists. But I'm not going to do it recursively, I'm going to do it iteratively. So my equals method is going to take in an object called other and compare it to this S-list. And if you are writing a dot equals method for a class, you might be really, really tempted to change the signature and make this object be an S-list. But you must resist that temptation. Do not make the parameter an S-list. Why is that? The reason is we want to override the equals method in the object class. And when you override a method in a superclass, you cannot change the signature at all. The signature has to be exactly the same as it is in the object class, or overriding will not work. And so typically that means that it's good behavior for the equals method to actually test whether the other is an S-list or not. So that's the first thing we're going to do. So we test whether other is an instance of S-list. And you will recall that that exclamation mark is the not, the logical not. And so this is saying if other is not an instance of S-list, then we know these two things aren't equal because they're not even the same class. But if we get past that, now we know we're comparing two S-lists. Therefore, it's safe to do a cast of other to something of static type S-list. And we want to do that cast so that we can use the S-list fields. And now the next thing I'm going to do is I'm going to compare the sizes of the two lists. So if this dot size is not the same as other dot size, then again the lists can't be equal, so I return false. But if we get past that, if we've gotten this far, then we know that we're comparing two S-lists with the same size, or at least the same size field. If the invariants hold, then they should be the same size. So now what we're going to do is have a loop that goes through both lists. So I'll have a variable for this head, and I'll have a variable for the other head. And I'll keep looping while they're not null. So I loop through all the nodes of one list and the nodes of the other list at the same time. And at each pair of nodes, I check the items in those two nodes, and I use dot equals to compare if those items are equal to each other. And if they're not, then we can return false. But if they are equal, we have to keep going. And so we advance both of our node pointers forward one list node. Until we reach the end of the list. And if we successfully reach the end of the list and we have not returned false, then now we know that the two lists actually encode the same items, and so we can return true. And that, with a few closing braces, is the end of the method. One thing I should say is that this implementation only is guaranteed to work if both S-lists satisfy the S-list invariance. So if you have a loop in one of the S-lists, don't count on this working. If the size fields are wrong in either S-list, don't count on this working. Any questions about this? Mm-hmm. Yeah, so if other is null, instance of works fine, and it will always return false. A null is an instance of nothing. Mm-hmm. Because it's faster, less writing. I don't want to write this if I don't have to. Yeah. All the stuff in this object is accessible unless I've stupidly shadowed it by naming a local variable exactly the same thing. Mm-hmm. When you're casting, you are not creating a copy of the object, no. When you cast, all it does is it changes the static type. And that means all casting really does is change how the compiler views that expression. Casting does not actually do anything at runtime at all, except maybe doing a dynamic runtime check that you really did give Java the type that you promised you would give it. Mm-hmm. If N2 is smaller than N1, then this crashes. Or I'm sorry, if N2 is, if the second list is longer. So there is code that checks the size field. Right here. So that checks whether the lists both have the same number of nodes, and it returns if they don't. So you should be fine as long as those size fields are correct. If the size fields are wrong, all bets are off. You can't expect this code to work. But if the size fields are correct, then this makes sure that you're not going to run out of nodes in N2. Other questions? Mm-hmm.
So while we're writing the dot equals, we're also calling it inside the method.
Mm-hmm.
Is that equals that call the one that we're writing recursively or the object?
Well, so you are calling dot equals recursively. In this example, you're calling dot equals recursively in one place. And whether or not that's actually recursive depends on what this item is. So if that item happens to be an S-list, if you have an S-list of S-lists, which is possible, then this really is a recursive call. But usually item will be something else like an integer, and so you're calling an equals method in a different class, which is going to be totally different. But it can be recursive. Mm-hmm.
You said not to have the argument as an S-list, and I was wondering what's wrong with overloading the equals operator as opposed to overriding?
You can overload the equals operator, you just won't get the benefits of overriding. So, well, the main benefit of overriding is that other classes will have objects. Let's say you have some other class that's using your equals method. So it has some object and it calls o.equals. Well, if you did not successfully override the equals method, then this is never ever going to call your equals method, because it doesn't even know your equals method exists because you failed to override correctly. So overloading equals in the slist class, that's something that you can only use inside the slist class or its subclasses. It's not gonna work for general purpose things that use equals. Mm-hmm. Say louder, please. If n1.item is null, well, you should never get to that point, because, well, if n1.item is null, then that's kind of violated another invariant we should have in our S list. One invariant of S lists that I didn't mention but should have is an S list node should never have a null item field. Uh-huh. You can't override the equals operator. I believe that's possible in C++, but not in Java. A brief moment to just touch on a completely different topic that's useful occasionally. Java has another kind of for loop that I haven't told you about yet, which is specialized to just iterate through array elements. So you have an array, you want to do something with each of its elements. A for each loop is a fast way to do that. So for instance, here's an array. And now I write this for loop. For, here I'm declaring an int variable that's going to iterate over each of these values, and then a colon, and then just the name of the array. And so what this will do is I will take on each of the different values in that array. So let me make clear that I is not iterating like a for loop, or like a normal for loop. It's not iterating from 0 to 5. You do not have the array index at all. What I is doing is it's taking on the values seven on the first iteration, then 12 on the second iteration, then 3 on the third iteration, and so forth. And so what this loop will do is it will print the string 7, 12, 3, 8, 4, 9. Again, you don't have access to the array indices as the for loop goes. If you want to know the indices of the numbers you're printing in that array, write a regular for loop. Don't use this one. Yes? If that's a string array, then yeah. So you can do exactly the same thing with an array of strings. Instead of saying for int I an array, if this were an array of strings, you would just say for string s array, and that would work too, if that were an array of strings. Mm-hmm.
Can you iterate things besides just arrays like strings?
You can do anything you have an array of.
But does it have to be an array? Like, can we iterate to other objects?
There is a way to iterate on certain types of objects that I'll talk about in a later class. We don't have the technology to do that yet, but that'll be coming. Mm-hmm. Can you do a 2D array? I don't think there's a notation for 2D arrays per se. I think you can write two different for each loops to go through the outer array and then the inner array. But I don't think there's a single for loop that will do a whole 2D array. Mm-hmm. After this exits, I think the value of I is 9 when this exits. though honestly I've never tested that, but I believe that's the case. One other thing I should say, this is a kind of nuisance, but you actually do have to have the declaration here inside the for loop. You would think that you would be able to write int I for I colon array, but no, you cannot. The compiler rejects this. I don't know why. Any more questions about that? I want to talk a little bit about testing your software, especially when you're doing a large project. Projects are generally easier to debug if you write lots of test code for them. And so I want to consider 3 different types of testing briefly. There's what's called modular testing, which will be the first subject. Integration testing, and finally something called results verification. So modular testing is when you test each method or class separately. Integration testing is when you test a whole bunch of methods and classes together. Results verification is when you either write code that checks that your data structures invariants are all true, or you write code that determines whether the output of an algorithm is correct. For modular testing, when you write a big program and it fails, it's really hard to figure out which part of the program failed. So it's usually wise to try to test each method you write separately. And you've already seen that we have code in a lot of the homeworks and projects that we've given you that do some testing for you, and that kind of testing is usually done by test drivers. There are usually 2 kinds of test code for modular testing. One is called test drivers, and one is called stubs. Test drivers are pretty obvious. They just call the code that you've written with different inputs, and then they check the results to make sure they're correct. And you've already seen lots of examples of this, as I said, in the labs and the homework. Generally, you should try to test every method you write, including the public and private ones. And that means that the test driver has to be inside the class that it's testing, so it can test the private methods. Usually, if you have a library, you put the test code in the main method, because the main method doesn't normally get called when the program is running and doing useful work. But if you have a program which is the main entry to your application, then the main method can't contain the test code because the main method is used to actually run your program, like the blur program in Project 1. So in that case, what you do is you write a test driver inside that method, and then you write a separate class whose sole purpose is to call that test driver. Stubs, on the other hand, are bits of code that are called by the code being tested. This is a less obvious idea that you might not think of. So there's sort of 3 reasons why you might want to do something like this. One reason is when you're implementing a really big project, sometimes you haven't implemented all the methods yet, but you can create a stub that fakes one of the methods by returning just really simple answers that may not be correct so that you can test the main method. Second reason is if you have one method that calls a second method and you don't know which one has the problem, you can replace the called method with a stub that just returns really simple answers in order to help test the main method and see if it works when you give it simpler input. And the third reason is, imagine that you are implementing an air traffic control system, and you want to see how well does your air traffic control system work if 10 planes take off at the same time. Well, it's really expensive to do a test where you actually have 10 planes take off at the same time. So what you want to do is fake it instead. You take whatever module gives you real-world data from the airline, and you replace it with a fake one that gives you fake information. This allows you to test on cases that are extremely rare in practice, and it allows you to have repeatable test data. So if you have a bug, you can run the same buggy software over and over again and get the same bug every time. Probably the hardest part of testing is integration testing, which is testing all the components together. In later lectures, I'm going to tell you about encapsulation, how to create a large project by building a small number of modules that fit together in good ways. The most important part of doing modularity well is to have very well-defined interfaces for how one part of your program calls another part of your program. And that's something you'll be learning as you do Project 2, especially since it'll be a group project. For integration testing, probably the most important thing is make sure you have really well-defined interfaces, and that'll be the subject of later classes. But the only other advice I can give you on integration testing, which is hard, is learn to use a debugger. We will have a debugger lab about midway through the semester when you're doing Project 2, but it's never too soon to learn debugging, and it may help you with your Project 1. The class reader that you can buy from Vic's Copy, the one with all the old midterms in it, also has instructions on using the debugger in the front matter of that reader. So definitely check that out. If you take a little time to learn it, there's a bit of a learning curve, but it really pays off in saving you a lot of debugging time later on. A third thing that's really nice to write when you're doing data structures or algorithms is result verifiers. And there are basically two kinds of result verifiers that check the results of your methods. There are what I'll call data structure integrity checkers. And what these do is they go through your code and check that all your invariants are satisfied. Which is why when you create a data structure, it's really useful to spend some time figuring out what your invariants are. That way you can check them. In Project 1, I am asking you to write a data structure integrity method, which is a method called check. And it just goes through your run length encoding and makes sure that there's nothing obviously wrong with your run length encoding. The other kind of result verifier is an algorithm result checker. And sometimes these are easy to do and sometimes they're not. But the idea is, suppose you write an algorithm that sorts a bunch of numbers. It's actually pretty easy then to write a piece of code that walks through your list of numbers and make sure that they're actually in a sorted order. Some algorithms are not so easy to verify, but sorting is, so it's worth doing. One thing that Java has built into the language is something called assertions that you can use in conjunction with your result verifiers. An assertion is a piece of code that tests whether an invariant is true or tests the result of an algorithm result checker. And so Java has an assert keyword that basically takes a Boolean, and if the Boolean is true, it does nothing. If the Boolean is false, then it throws an exception. And so you might use this when there's certain things that you know should always be true, and you want to get an error message if they're false. So let's suppose you have some loop, and at a certain point of the loop, you know that some value x should always be equal to 3 at that point. Well, Java makes it very easy to just drop a line in your code that says assert x equals 3, and if x turns out not to be 3 when you hit that point, it'll print an error message and dump the stack and quit running for you. You can also use the assert keyword in conjunction with more interesting things like calls to result verifiers and integrity checkers. Like, for instance, suppose that I have a count length method that walks through my list and counts up all the nodes. I want to use that to check whether or not the size field is correct. So I assert that the size field is equal to the actual count of nodes, and this will just do the check from time to time. The assert keyword also allows me to add my own error message if I want. By putting a colon there, and then putting the error message after the colon. And what's useful about assertions is that you can actually turn them on or off when you run the compiler, and so you can get rid of them without actually editing your code. And so if you want your assertions to be in your code when it's running, then you write java-ea when you compile. EA stands for enable assertions. And then when you've finished testing your code and you know it works, and now you want to provide a release version that runs fast and doesn't waste time checking things, then you can just turn them off by compiling again with java-da for disable assertions. And that usually gives you greater speed. Though one thing you have to be careful about is that since it does not run the assertions at all, when you disable the assertions, this count length method will never be called. So you must make sure that the code that is in your assertions is not important for your program to work. There's someone who wants to make an announcement before we leave. But before we do that, I just want to give you one final thought, which is there is a lot of test code in real-world projects. In real-world software development, most companies that sell products have more lines of test code than they have lines of code in the actual product. And who do you think writes all of that test code? I think you can guess who writes all of that test code. Stanford graduates.